Welcome to the APL quest. See APL Wiki for details. Today's problem is the last from the 2015 round of the APL problem-solving competition. We are to generate Pascal's triangle, which is pretty simple, but the catch here is that we want it to also look nice for human readers, and a triangle doesn't fit nicely into a rectangular array. So instead of having it numeric, as Pascal's triangle consists of numbers, we are to create a character matrix where the lines are approximately centered. There are two steps to this problem. The first is generating the data, and then there's centering the lines. So let's split it into those two parts. Pascal's triangle has a classic elegant solution. It is simply the binomial coefficients outer product on all the numbers from 0 to n. There's a problem though with this triangle. It's sideways and it's padded with these zeros. We can do something about that, of course, but it makes it a little bit less elegant. So first we transpose it, and that gives us the rows at least as rows. And then we need to remove the zeros. So on each row, that is on each sub-array of rank 1, we want to be without zeros. But the problem is that we're going to pad again with zeros if we try to apply this just like this. So that didn't get us anywhere. Therefore, we must immediately format it as a character array, and now the padding will instead be done with spaces. And this gives us the first and flat approach to creating the data that we want, and the next part is then to align the rows so that to be centered, and we'll come back to that. Another approach is a nested one. We start off the same way by generating all these indices, but instead of doing an outer product, we kind of doing half an outer product. So again, we want the same indices up to whichever n that we are at now, combined with that number. And that gives us kind of a triangle with each row getting longer and longer. And then since we are going to deal with character data and have it the nested equivalent of the previous shown flat result, then we're going to format each one. It looks the same, but these are actually character vectors. And this we can call n because it's the nested solution. We can also avoid repeating ourselves. We have here 0, iota, and we have over here 0, iota. So we could say this is kind of like an inclusive iota in here, and then we can use that name over here. It comes out and it represented exactly the same, but just the way of stating it is a little bit shorter. And now that we have the data, let's look at actually centering it. So let's go back first to our flat matrix with the trailing spaces. So one strategy for centering it is looking at how many trailing spaces are there. There are 4 on this line and there are 6 on this line. So if we take half of those on each line and then rotate the entire row, so we'll remove the last trailing spaces and put them at the front. And here we have 6. We're removing the trailing 3 and putting it in the front. Then we end up having something that looks centered. How can we do this? Well, we need to count how many trailing spaces there are. If we make a Boolean matrix of where we have spaces, and then make sure that we do that in the reverse, so now it becomes leading spaces, we can do AND reductions on each line to isolate the leading spaces, which are actually the trailing spaces, and then we can sum that to see how many leading, that is, trailing spaces there are. And then we want only half of that, So these are how many steps to rotate. It could be that the number is odd, not a number of spaces odd, and therefore we get a half. So to be safe, let's just round this off. The problem specification also says that it can be one more or less, so it's not important how exactly we round it up or down. There's definitely no reason to round off to closest because it's always going to be a whole number or half. Okay, so now we want to rotate this many steps, but rotation, normal rotation APL rotates from the front to the rear, but we need to rotate from the rear to the front, so we need to negate this, and then if we give a name or an argument name to the matrix that we're operating on, then we can simply do a horizontal rotate using these values as the rotation amount, and that gives us our centered matrix. So this is rotation using the flat, and this is the whole thing is one large atop, where the right function, right tine, is this f generator function that we created before, and then the left tine is the centering thing. And we can even see this classic approach. The idea is highlighting this to be a dialog idiom, which means it doesn't actually go through each of these three operations. Instead, it recognizes this as a whole idiomatic expression and computes the trailing spaces directly for some extra performance benefit. Let's say that we instead started with the nested array. Now here aren't any spaces that we can count and operate on, but we can look at the length. And remember that these are character vectors. So if we get the length of each one of them, then we have those here. And we can see that even though it's only two numbers, it's length 3 because there's a space in between as well. And so what we want to do here is we want to rotate around on the whole matrix, and we can create the matrix, the flat matrix, simply by mixing. So here we have it with the spaces. So we're still going to rotate, but we're going to compute the amount of rotation based on the nested representation of it. So we have the length of each, and then on the length of each, how much do we need to rotate? Well, the full width is the length of the last one, and all the lengths are, it's just the same thing, that's the argument here, and we want half of the difference between them to be the amount that we rotate with. So this is the length, and this is the length of the longest one, and this gives us these negative numbers. And I've done it negative like this. Of course, we could if we subtract the other way around, we get it the corresponding positive numbers. But since we're going to do a negative rotation amount, we might as well just keep it negative from the beginning. And then we divide that by 2 as before, and we can round it off. Again, it doesn't really matter how we round it. So this is the amount of rotation that we need to do on each one. And then we use this to rotate, but not the argument itself, because that's nested. We want to rotate the mix of the argument. And then since this is a, so then we have an the top over here, and then we just need to swap the arguments over here. We have it here. This is on the top, 2 pieces. We can't use the top operator here because the left function is complex. But since this is the post-processing on the result of the tally of each, it could also be the pre-processing of the swapped rotation. So we can replace this with a jot over here, and it would be the same thing. So this is a way of using rotation with a nested representation. Again, on the top, this is the centering function, and this is the generating function. So now we used rotation, but we can also use take. So take has this interesting thing that you can, what I sometimes call overtake. So let's say we have ABC. If we take the last 5 elements from that, then that pads us with 2 spaces at the beginning. And we can use this to our advantage. And the same thing goes if we take from the beginning, then we get trailing spaces over here. So for this to work, we can't already have them all the rows be the same length in the flat representation. So we have to use the nested representation. And now we are going to start off the same way. We get the length of each one. And then we need to compute what is the length that we want to take from the rear of each one, which is going to be the length it already has plus half of the difference between the longest one and the current one. That's going to add half of those potential spaces on the left. Okay, so let's state that. The current length plus half of the difference between the longest one, which is the same thing as the last one, minus the current length. So these are the lengths that we need to take from each one. Of course, this needs to be negative. And then we need to make sure that we don't have any halves, so we can round that up as well. And then the only thing that's missing is that we take from each one with this amount, and these are the nested things. So now we have padded them with leading spaces so that they will fit each other, and then we can just mix and we get the character matrix that we're looking for. However, we can simplify this quite a bit actually. If we think about it, then we have the amount itself plus half of the difference between this constant value, so to say, the last one, and the amount itself. In other words, we are here removing from the part that we are adding, which means that we can also see this as half of the last element, the longest one, plus only half of the value itself, because we're adding the whole thing and then we're subtracting half of it. So then what we can do is just add half to begin with and not add a whole one and subtract the half one. And we can keep going. We are here negating this half, but we could include, so to say, this sign change in the division, which is a type of multiplication. So if we divide by -2 instead, that's the same thing. But another way we could do it, since the only thing we need to affect is a sign change, then instead of adding, so to say, these lengths, we can add their negation, and instead of adding the last one, we can subtract the last one. So that affects also a sign change on the whole thing, and we get the same result. And this is another very nice way of creating our matrix. So we can call this the overtake. So it uses take on the nested representation. Again, on the top, this time we have a defn on the left, and then our original generating function on the right. Okay, so how do they compare to each other? Well, there's not really any upper limit to what we can do here, but let's increase the print precision to the maximum that our 64-bit floats will allow. And then we can do triangles up to, say, order 50 or so. Copy in CMPX from the defense workspace. And let's try everything for n's up to 50. We can stick a 0 in front as well. And then we want to compare. This was the rotation using the flat on each, and we want the rotation using the nested on each. And then we wanted to have the using take on the nested on each. Oh, so we can see that the nested approaches here are, well, approximately half the runtime of the flat approach, and that's exactly what we predicted to begin with, because we are generating only half the triangle, slightly more than half the triangle, because we need a diagonal, and that is the overwhelming amount of computations. Then to here, and we are using just slightly over half of the runtime in the nested approach. So even though it's a good rule of thumb that when you're doing APL, you want to stay flat, you have to also recognize when is flat actually flat. In this case, we were processing each row separately, and that really negates all the benefit of staying flat. Thank you for watching.